Now, in this lecture, we'll answer on two questions. In the first question, we'll find out the radius of this circle that is inscribed by the right triangle, triangle ABC. And in the second question, we will find out the area of the blue right triangle, triangle DCB that is inscribed by the quarter circle. We start with the first question. In the drawing, we have the right triangle, triangle ABC. Side AB equals to 8 units. Angle ABC equals to 90 degrees. We also know that the lengths of side BC and side AC of triangle ABC are integers. And we want to find out the radius of this circle that is inscribed by the right triangle, triangle ABC. So first of all, we will define side BC as A. And the hypotenuse AC is B. And then we will use the Pythagoras theorem in the right triangle, triangle ABC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars for the right triangle, triangle ABC. Here, by PT is a relation for Pythagoras theorem. We get that AC square equals to AB square plus BC square. We repeat again, in the right triangle, triangle ABC, according to the Pythagoras theorem, we get that AC square equals to AB square plus BC square. AC equals to B, therefore AC square is B square. And it is equal to AB square. AB is 8, so AB square is 8 squared, that is 64. Plus BC square. BC equals to A according to definition, therefore BC square is A squared. So in conclusion, according to equation number 1, we found out that B square equals to 64 plus A square. Here we subtract A square from this equation, equation number 1. And we get that according to equation number 1, B square minus A square equals to 64. So here we have the algebraic identity that b square minus a square equals to b plus a times b minus a. Therefore, we substitute b squared minus a squared by b plus a times b minus a. And according to equation number 1, it is equal to 64. According to what is given in the question, if AC and BC are integers, but AC equals to B and BC equals to A, it means that A and B are integers, and the second thing is that A and B actually A and B are the lengths of the sides of the right triangle ABC. Therefore, actually A and B, they are lengths, and the lengths, they must be positive numbers. So from 1 and 2, we will derive that A and B are positive integers. So if A is a positive integer and B is a positive integer, it means that B plus A will be also a positive integer, because when you add two positive integers to each other, the result must be a positive integer. And the second thing that we can deduce from the fact that A and B are positive integers, that B plus A will be greater than B minus A. Okay, because when you add two positive integers to each other, the result always will be greater than the case that when you subtract the two positive integers from each other. And we also know that B is the hypotenuse of the right triangle ABC, and the hypotenuse is always greater than the perpendiculars. That is to say, B is greater than A. It is always true that B must be greater than A. So if we subtract A from this inequality, we get that B minus A is greater than 0. That is to say, B minus A is a positive number, but because of the fact that B is a positive integer and A is a positive integer, it means that B minus A, if B minus A is a positive, it must be also a positive integer. So we can conclude from it that B minus A is a positive integer, Actually, according to question number 1, that b plus a times b minus a equals to 64, it means that if you take two positive integers and multiply them by each other, the result will give us 64, according to equation number 1. And actually, there are not a lot of options of the positive integer that you can take, the two positive integers that you can take, and will give you 64. So we write down all the positive integers that are possible, that when you multiply one by each other, you will get 64. The first couple will be 1 and 64. The second couple will be 2 and 32. The third couple will be 4 and 16. The fourth couple will be 8 and 8. The fifth couple will be 16 and 4. The sixth couple will be 32 and 2, and the last couple will be 64 and 1. So we have actually 7 couples in total, 7 positive integers that if you multiply one by each other, we get 64. Okay? But we also know that according to this inequality, b plus a is greater than b minus a. That is to say, the first column, that is b plus a, must be greater than the second column, b minus a. That is to say, out of those 7 options, the only valid option will be when the first column is greater than the second column. Otherwise, the option will not be valid. Because b plus a must be greater than b minus a. So we check in which couples b minus a is greater than b plus a is greater than b minus a. Here, 1 is not greater than 64. This is to say it is not a good possibility. 2 is not greater than 32. That is to say it is not a good possibility. 4 is not greater than 16. This is also not a good possibility. 8 is not greater than 8. Therefore, it is not a good possibility. But 16, that is b plus a, is greater than 4, that is b minus a. So this is a good option. 32 is also greater than 2. That is to say it is a good option. And finally, 64 is greater than 1. It means that it is a good option. So in conclusion, we have only 3 options that left that can be the answer to our question for b plus a and b minus a. In the next step, we will add the two numbers together in order to find out what is the result of adding the two numbers together. So we add b plus a to b minus a, and we get that b plus b is 2b and a minus a is 0. So when we add the two numbers together, we get 2b. b is a positive integer, therefore 2b is an even number. That is to say, when we add the two numbers together, b plus a and b minus a, the result must be an even number. Otherwise, if the result is not an even number, it is not a good option. Okay, so we check now which possibilities for the four options that we have for the solution to the question are good possibilities. That is to say, they will give us a number that is an even number. So the first option is 16 plus 4, that is 20. As 20 is indeed an even number, therefore it is a good possibility. And then we have also 32 plus 2 is 34. 34 is also an even number, therefore it is also a good possibility. And finally, 64 plus 1 is 65. It is not an even number, it is an odd number, therefore this is not a good possibility. We cancel this option, so we left only with two possibilities for b plus a and b minus a. So write them down. According to the first option, according to the first option, b plus a equals to 16, while b minus a equals to 2, and according to the second option, b plus a equals to 32, while b minus a equals to 2. Here, according to the third option, b minus a equals to 4. Okay. And according to the second option, b minus a equals to 2. Okay. So here we'll add the first equation to the second equation, and we get that b plus b is 2b and a minus a is 0. So in this side of the equation we have 2b, in the other side of the equation we have 16 plus 4, that is 20. So if we know that 2b equals to 20, we divide this equation by 2, and we get that b equals to 20 over 2 is 10. So b equals to 10 units, and according to this equation, b plus a equals to 16. We subtract b from this equation, and we get that a equals to 16 minus b, but we have already found out that b equals to 10, so we substitute b by 10, and we get that a equals to 16 minus b, and b is 10, so it is 16 minus 10. 16 minus 10 is 6. So in conclusion, we found out that A equals to 6 units and the hypotenuse B equals to 10 units. So those are the values of the sides of the right triangle, triangle ABC, that inscribes the circle. This is the first option. According to the second option, we add equation number 1 to equation number 2 and we get that B plus B is 2B and is equal to A minus A is 0. On the other side of the equation we have 32 plus 2 is 34. So if we know that 2B equals to 34, we divide this equation by 2 and we get that B equals to 34 over 2 is 17. So the hypotenuse B is 17. And according to this equation, B plus A equals to 32. We subtract A from this equation and we get that B equals to 32 minus A. Actually, we subtract B from this equation and we get that A equals to 32 minus B. But we already found out that B equals to 17 units, so we substitute B by 17 and we get that A equals to 32 minus B and B is 17, so it is 32 minus 17. 32 minus 17 is 15, so A equals to 15 units and the hypotenuse B equals to 17 units. So I will draw the two right triangles here. They are the answer to the questions for the triangles that give us the radius of the circle that is described by those two right triangles. Okay. So here, according to the first option, this is the triangle ABC. Now it is given as the question that side AB equals to 8 units. We just right now found out that BC that is equal to A, according to our definition, it is equal to 6 units, and the hypotenuse AC that is equal to B, it is equal to 10 units. And actually inside this right triangle, triangle ABC, we have a circle that is inscribed by this triangle, by this right triangle. This is the circle that is inscribed by the right triangle, triangle ABC. And our mission is to find out the radius of this circle that is inscribed by this specific triangle, triangle ABC. So we define the radius of this circle as capital R. And we find out the radius of this circle. The second option is we have another right triangle that is a solution to the question. This is the right triangle ABC. It is given us the question that side AB equals to 8 units. We just right now found out that side BC that is equal to A, according to our definition, equals to 15 units. And the hypotenuse AC that is equal to B, according to our definition, it is equal to 17 units. Inside this right triangle, we have a circle that is inscribed by this right triangle, triangle ABC. And our mission is to find out the radius of this circle that is described by this right triangle, triangle ABC. By this specific right triangle, triangle ABC. So, in order to find out the radii of those two circles that are inscribed by those two right triangles, here we take a right triangle, triangle ABC, that could be any triangle, any right triangle. And we will find out the radius of this circle that is inscribed by triangle ABC, that could be any right triangle. And after we find out the radius of this circle that is inscribed by the right triangle ABC, we use the formula in order to find out the radii of the two circles that are inscribed by the two right triangles that we found out. So, first of all, we will define side AB of the right triangle, triangle ABC, as A. We define side BC of the right triangle, triangle ABC, as B. And we will define the hypotenuse AC of the right triangle ABC as C. I repeat again that because of the fact that triangle ABC could be any triangle, any right triangle, it means that we can implement the formula that we get for the radius of the circle that is described by this right triangle in our two specific right triangles. It could be any right triangle, and especially our two right triangles. Okay. We define the center of this circle as O. We define the point of tendency of tangent AB with this circle as N. We define the point of tendency of tangent BC with this circle as M. We define the point of tendency of tangent AC with this circle as L. In the next step, we join points O and N together by a straight line. So what is the definition of line segment ON? Actually, point O is the center of this circle, point N is the point of the circle itself. This is exactly the definition of a radius. That is to say, ON is the radius of this circle, So it is equal to capital R according to our definition. And here we have actually rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have the radius OM that is drawn to the point of tendency, and whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. So if AB is perpendicular to NO according to rule number 1, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Likewise, according to rule number 1, we have the radius OM that is drawn to the point of tendency, that is to say, it is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. So if BC is perpendicular to MO, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees. So actually in quadrilateral ONBM we have 3 right angles. 1, 2, 3. And the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the 4th angle, that is actually angle NOM. This angle in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, so 270 degrees plus the size of this angle must be equal to 360 degrees. If we subtract 270 degrees from the equation, we get that the missing angle NOM equals to 90 degrees. So actually, we found out that inside quadrilateral NOBM we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral NOBM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. So that is to say, in rectangle NOBM, NO must be equal to BM. Okay? But we already found out that NO equals to R. And NO also equals to BM, therefore BM must be also equal to R. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get here that NB equals to OM, but OM equals to R, and NB equals also to OM. Therefore, NB must be also equal to R. So actually we found out that for the other NOBM it is not a rectangle but a square because all of its sides are equal to each other. What is the length of line segment AN? Here, from the drawings it is very easy to see that AN equals to AB minus MB. AN equals to AB, that is A, minus MB, that is R. So in conclusion, AN equals to A minus R. Likewise, we find out the length of line segment MC. Line segment MC will be equal to BC minus BM. Again, BC minus BM equals to MC. So MC equals to BC, that is B, minus BM, that is R. So in conclusion, we found out that MC equals to B minus R, while AN equals to A minus R. Well, we also have rule number 2 here. According to rule number 2, the lengths of two tangents from a common extra point to a circle are equal. So if we focus On the current standpoint, point A, we have two tangents to this circle, tangent AN and tangent AL. And according to rule number 2, AN equals to AL. But we have already found out that AN equals to A minus R. And AN also equals to AL, therefore AL must be also equal to A minus R. In the next step, we focus on the current standpoint, point C. From the current standpoint, point C, we have two tangents to this circle, tangent CM and tangent CL. And according to rule number 2, they are equal to each other, that is to say CL equals to CM. CL equals to CM, CM equals to CL, but we have already found out that CM equals to B minus R. Therefore, CL must be also equal to B minus R. So in conclusion, we found out that CL equals to B minus R and AL equals to B minus R. So what is the length of the hypotenuse AC? The length of the hypotenuse AC from the drawing, it is very easy to see that AC equals to AL plus LC. AL plus LC. So AC equals to AL. AL equals to A minus R. So we substitute AL by A minus R plus LC. LC equals to B minus R. So we substitute LC by B minus R. So in conclusion, we found out that the hypotenuse AC equals to A minus R plus B minus R. According to our definition, the hypotenuse AC equals to C. So we substitute AC by C and we get that C equals to A minus R plus B minus R. That is to say C, the hypotenuse C equals to A plus B minus R plus minus R is minus 2R. So C equals to A plus B minus 2R. We will add 2R to this equation and we get that C equals 2R plus C equals to A plus B. Here we subtract C from this equation and we get that 2R equals to A plus B minus C. Here we divide this equation by 2 and we get that the radius we are looking for, R equals to A plus B minus C over 2. Okay, so we actually found out a general formula to find out the radius of any circle that is inscribed by a right triangle, triangle ABC, that could be any triangle. And because of the fact that triangle ABC could be any triangle, it is especially could be our two triangles. That is to say, we will use the new formula that we found in order to find out the radii of the two circles that are inscribed by our two specific right triangles. So here we found out that the formula for the radius of any circle that is inscribed by a right triangle, it is equal to A plus B minus C over 2. Here A plus B is the sum of the perpendiculars, minus C is minus the hypotenuse over 2. So the radius of this circle that is inscribed by this specific right triangle, triangle ABC, will be equal to A plus B is 8 plus 6, minus C is minus the hypotenuse that is 10 over 2. So R equals to 8 plus 6 is 14, and 14 minus 10 is 4, and 4 over 2 is 2. So we found out that the radius of this circle that is described by this specific right triangle, triangle ABC, equals to 2 units. So we can write here that R equals to 2, and we'll find out the radius of the other circle that is described by this specific right triangle. R will be equal to A plus B is 8 plus 15, minus C is minus the hypotenuse, that is 17 over 2. So here 8 plus 15 is 23, and 23 minus 17 is 6, and 6 over 2 is 3. So we found out that the radius equals to 3 units. So we have two solutions to this question. The first solution is that the radius of the circle that is described by this specific right triangle triangle, ABC could be equal to either 2 units or 3 units. Okay, that is the answer to the question. Here, the radius of this circle that is described by this specific right triangle triangle ABC could be equal to either 2 units or 3 units. Okay. We finish with the first question. In the next step, I will present to you the second question, and we will solve the second question in 2 different methods. In the drawing, we have a quarter circle, side OB equals to 2 units, AD equals to DO. Inside this quarter circle AOB, we have this light blue triangle, triangle DCB, and we want to find out the area of this blue right triangle, triangle DCB. We'll start with the first method. First of all, because of the fact that AOB is a quarter circle, it means that this angle equals to 90 degrees. Point O is the center of the quarter circle. OB is the radius of the quarter circle that is equal to 2 units. So AD equals to DO, and AO itself is the radius of the quarter circle that is equal to 2 units according to what is given as the question. So actually here AO side AO, it is equal, for drawing it is very easy to see that it is equal to AD plus DO, and it is equal to OB, that is the radius of the quarter circle, and we know that it is equal to 2 units. So if we define AD as x, then DO will be also equal to x because they are equal to each other. So here, according to our definition, AD equals to x, and DO also equals to x. So we have x plus x equals to AD plus DO equals to AO equals to OB equals to the radius that is equal to 2x plus x is 2x, and 2x equals to 2 units according to this long equation. We divide this equation by 2 and we get that x equals to 2 over 2 is 1. X equals to 1 unit, so we can write down here that x equals to 1, so AD equals to 1, and the O that is equal to x, it is equal to 1, so the O also equals to 1. Okay, in the next step we complete the quarter circle to a circle. And we'll extend the radius BO by a straight line until okay, first of all I will finish to draw the circle itself. So we created from this quarter circle a circle, and then we'll extend the radius BO by a straight line until it touches the circle, and we'll define the touching point of the extended radius BO, and this circle is P. And in the next step, so here point O is the center of this circle, point P is the point on the circle itself. This is exactly the definition of a radius. That is to say, PO is the radius of this circle that is equal to 2 units, because the radius of the circle is the sum of the radius of the quarter circle, and they are equal both to 2 units according to what is given as the question. So we extended the straight line BO by a straight line, and so the result BP must be also a straight line. Okay? So we have here chord BP that passes for the center of the circle, that is to say it passes for point O. Any chord that passes through the center of the circle is defined as the diameter of the circle. So line segment PB is the diameter of the circle. Okay. In the next step, we will extend side CD by a straight line until it touches the circle, and we don't know where the extended side CD will touch the circle, so we will assume that the touching point of the extended side CD with the circle will be at this point. That we define the touching point of the extended side CD with the circle as point X. Okay? So this is our assumption that the touching point of the extended side CD with the circle is at point X. So actually we created here peripheral angle BCX. BCX is peripheral angle because it touches the circle at point B and at point X, and also the vertex is at point C. Therefore it is absolutely a peripheral angle. So angle BCX is a peripheral angle. I'll write it down. According to our construction, we created peripheral angle BCX, but according to what is given us the question, the size of peripheral angle BCX that we created, it is equal to 90 degrees. Okay, so peripheral angle BCX equals to 90 degrees, and it touches the circle point B, C, and X. Okay, but because of the fact that we know that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. It means that peripheral angle BCX that is equal to 90 degrees must rest on PB, that is the diameter of the circle. But you can see from the drawing that peripheral angle BCX doesn't rest on the diameter, but on BX. So therefore we have here a contradiction that peripheral angle BCX must rest on the diameter of PB, but it doesn't rest on the diameter. So in order to avoid, to solve the contradiction, we must conclude that point X merge with point P. Point X must merge with point P, and so here, that is to say, the straight line, when we extend side DC by a straight line, it must touch the circle at point P. Why? Because according to our conclusion, point X must merge with point P. Okay? And in this way, we will avoid the contradiction. Why? Because we have here peripheral angle BCP that is equal to 90 degrees, and indeed it rests on the diameter of this circle that is PB. Okay? Okay? I repeat again, in order to solve the contradiction here, to avoid the contradiction, point X must merge with point P. In this way, peripheral angle BCP that is equal to 90 degrees indeed rests on the diameter of this circle that is PB. Okay? So PB is the diameter of this circle, therefore it is absolutely a straight line. PB is the diameter, it must be a straight line, and we know that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on point O, the upper side of the straight line PB, here the sum of the angles must be equal to 180 degrees. So which angles we have here? We have here 90 degrees plus angle AOB, total AOP. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. So here, 90 degrees plus angle AOP equals to 180 degrees. So if we subtract 90 degrees from the equation, we get that the missing angle AOP also equals to 90 degrees. So this is the right angle, is equal to 90 degrees. Okay, so here We focus on the right triangle, triangle PDO. On the right triangle, triangle PDO, by PT is the evaluation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, PD square equals to DO square plus PO square. I'll repeat again, in the right triangle, triangle PDO, according to the Pythagoras theorem, PD square equals to DO square plus PO square, so PD square equals to here DO equals to 1, so DO square is 1 squared, that is 1, plus PO square. PO is 2, so PO square is 2 squared, that is 4. So in conclusion, we found out that PD square equals to 1 plus 4, that is 5. We take out of this equation and we get that PD, the hypotenuse PD equals to square root of 5 units. So you can write here that PD equals to square root of 5 units. We will repeat on the same process of the right triangle, triangle DOB. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, dB square equals to dO square plus OB square. So dB square equals to dO square. dO is 1, so dO square is 1 squared, that is 1, plus OB square. OB is 2, so OB square is 2 squared, that is 4. So in conclusion, we found out that dB square equals to 1 plus 4, that is 5. We take out of this equation and we get that dB equals to the square root of 5 units. Okay, dB equals to the square root of 5 units. In the next step, we will extend the radius AO by a straight line until it touches the circle. We define the touching point of the extended AO in the circle as Z. And then I will present to you rule number 1, and we implement rule number 1 in our drawing. According to rule number 1, if we have a circle inside this circle we have chord AB. This is chord AB. Intersects with chord CD. This is chord CD. And the intersection point is at point O. Again, chord AB intersects with chord CD at point O. So if this is the data that has been given to us, then the following equation is true, that AO times OB equals to CO times OD. Repeat again on rule number 1. According to rule number 1, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We actually can implement rule number 1 in our drawing. Why? Because in our drawing, we have chord AZ, intersects with chord CP, at point D. I repeat again, here, chord AZ intersects with chord CP at point D. Therefore, according to rule number 1, we get that AD times DZ AD times DZ equals to CD times DP. I repeat again, according to rule number 1, AD times DZ equals to CD times DP. Okay, so AD is 1, and here, what is the length of line segment OZ? O is the center of the circle, and Z is the point of the circle itself. This is exactly the definition of a radius. That is to say, OZ is the radius of this circle that is equal to 2 units according to what is given in the question. So what is the length of DZ? DZ equals to 1 plus 2, that is 3. So DZ equals to 3 units. And it is equal to CD. CD is the missing line segment, so we leave it as it is. Times DP. DP equals to the square root of 5 units. So we substitute DP by square root of 5 units, and we get that 3 equals to square root of 5 times CD. We divide this equation by square root of 5, and we get that CD, the missing line segment CD, equals to 3 over square root of 5 units. Okay. CD equals to 3 over square root of 5 units. In the next step, we'll implement the Pythagoras theorem on the right blue triangle, triangle DCB. So according to the Pythagoras theorem on the right triangle, triangle DCB, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is dB, therefore the square of the hypotenuse is dB square. That is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to dC square plus CB square. I'll repeat again, in the right triangle DCB, according to the Pythagoras theorem, dB square equals to DC square plus CB square. So dB equals to the square root of 5. Therefore, dB square is square root of 5 unit square root of 5 squared, that is square root of 5 squared, that is 5. And DC equals to 3 over square root of 5. Therefore, DC square equals to 9 over 5 plus CB squared, that is the missing 9 segment, so we'll leave it as it is. Here we subtract 9 over 5, 9 fifths from this equation, and we get that 5 minus 9 fifths equals to CB square. Here we'll multiply 5 by 5 and then we'll divide it by 5 in order to have a common factor with this expression. 5 times 5 is 25. So in the numerator we have 25 minus 9 over 5. That is equal to CB square. (25 minus 9 is 16, so 16 over 5 equals to CB square. Here we'll take out of this equation and we'll get that CB equals to the square root of 16, that is 4 over square root of 5. So in conclusion, we found out that CB equals to 4 over square root of 5. Now it is very easy to find out the area of the blue right triangle, triangle DCB. The area will be equal to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. So the area of the right blue triangle, triangle DCB, will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. So DC equals to 3 over square root of 5 units times CB, that is equal to 4 over square root of 5 units, all divided by 2. 3 times 4 is 12, so in the numerator we have 12, in the denominator we have square root of 5 times square root of 5 is 5, and times 2. Here 12 over 2 is 6, so in the numerator we have 6, in the denominator we left only with 5. So in conclusion, the area of the blue right triangle, triangle DCB, it is equal to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. Okay, we finished with the first method. In the next step, I will present to you the second method. So according to the first method, we have already found out that angle AOB equals to 90 degrees. And we have already found out that point O is the center of the quarter circle. AD equals to 1 unit. DO equals to 1 unit, and the radius of this quarter circle is equal to 2 units. We'll complete the quarter circle to a semicircle. Here we'll extend the radius BO until it touches the semicircle at point P. Point O is the center of the semicircle, point P is the point on the semicircle itself. This is exactly the definition of a radius. That is to say, PO is the radius of this semicircle that is equal to 2 units, according to what is given as the question. According to the first method also, we already proved that PB is the diameter of this circle. Why? Because it passes from point O, that is the center of this circle. Any chord that passes from the center of the quarter circle or the center of the semicircle, it is defined as a diameter. So I can write down that PB is the diameter of the quarter circle. We'll extend side CD by a straight line until it touches the circle, and we've already found out in the first method that if we extend side CD by a straight line, it must touch the circle or the semicircle at point P and only at point P. Okay. According to the first method, angle AOP equals to 90 degrees. In the first method, we have already found out that the hypotenuse PD equals to the square root of 5 units in the right triangle PDO, and the hypotenuse DB also equals to the square root of 5 units in the right triangle DOB. We will define angle DPO as theta, and we know that in the right triangle DPO, angle DPO equals to theta, angle DOP equals to 90 degrees. Therefore, angle PDO must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle DPO to 180 degrees. Angle PDO must be equal to 90 degrees minus theta, because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. So if you focus on the right triangle PCB, angle CPB equals to theta, angle PCB equals to 90 degrees, and the angle PBC must be equal to 90 degrees minus theta, for the same reason exactly that this angle equals to 90 degrees minus theta. This angle must be also equal to 90 degrees minus theta. In order to complete the sum of the angles in the right triangle PCB to 180 degrees, this angle must be equal to 90 degrees minus theta. So in the next step, we will prove that the right triangle PDO is similar to the right triangle PCB. Okay. So we prove that the right triangle PDO is similar to the right big triangle PCB. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So you can write down that angle POD, this angle equals to angle PCB, this angle, and they are both equal to 90 degrees, therefore they are equal to each other. I'll repeat again, angle POD equals to angle PCB equals to 90 degrees. In addition, we have those two angles that are both equal to 90 degrees on theta, therefore they are equal to each other. So angle PDO this angle equals to angle PBC, this angle, and they are both equal to 90 degrees from theta, therefore they are equal to each other. I'll repeat again, angle PDO equals to angle PBC, and they are both equal to 90 degrees from theta, therefore they are equal to each other. And finally, this angle is a common angle that belongs to both triangles, so this angle equals to itself. So angle DPO equals to angle CPB, and this is equal to theta, so it is angle DPO equals to angle CPB equals to theta. It is a common angle that belongs to both triangles. So in conclusion, we found out that all three angles of triangle PDO can go into all three angles of triangle PCB, therefore triangle PDO is similar, this is the sign of similar, to triangle PCB according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PD over PB equals to DO over CB, and it is also equals to PO over PC. And again, from the fact that the two right triangles are similar to each other, we conclude that PD over PB equals to DO over CB equals to PO over PC. So here, PD equals to a square root of 5 units over PB, and PB equals to 2 plus 2, that is 4. DO equals to 1. CB is the missing line segment, so we leave it as it is. And it is equal to PO. PO is 2 over PC. PC is square root of 5 plus DC. So in conclusion, we found out that 5 over square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. We will derive from this long equation, the first equation, that square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation, equation number 1, and we'll get that square root of 5 times CB equals to 4. We will divide this equation by square root of 5, and we will get that CB equals to 4 over square root of 5. So if we know that CB equals to 4 over square root of 5, in the next step we will implement the Pythagoras theorem on the right blue triangle, triangle DCB. On the right blue triangle, triangle DCB, according to the Pythagoras theorem, dB squared equals to CB squared plus DC squared. Repeat again, the right triangle, triangle DCB, the right blue triangle, triangle DCB, according to the Pythagoras theorem, dB squared equals to CB squared plus DC squared. So dB squared equals to CB squared. CB is 4 over square root of 5, so CB squared is 16 over 5. And this is the missing side, so we leave it as it is. So dB squared equals to 16 over 5 plus DC squared. dB equals to square root of 5, so dB squared is 5. So 5 equals to 16 over 5 minus DC squared. We will subtract 16 fifths from this equation, and we will get that 5 minus 16 fifths equals to DC squared. Here we multiply 5 by 5 and then we divide it by 5 in order to have a common factor with this expression. And we find out that 5 times 5 is 25 minus 16 over 5. That is equal to DC squared. (25 minus 16 is 9, so 9 over 5 equals to DC squared. We take out all of this equation and get that DC, the missing 9 segment, equals to the square root of 9, that is 3, over square root of 5. So we found out that DC equals to 3 over square root of 5. Now it is very easy to find out the area of the blue right triangle, triangle DCB. It will be equal to the base of the triangle that is DC times the height of the base that is CB over 2. So the area of the right blue triangle, triangle DCB equals to the base of the triangle that is DC times the height to the base that is CB over 2. DC equals to 3 over square root of 5, CB equals to 4 over square root of 5, all divided by 2. 3 times 4 is 12, so in the numerator we have 12. In the denominator we have square root of 5 times square root of 5 is 5 over times 2. 12 over 2 is 6, so we have 6 in the numerator, and in the denominator what is left is only 5. So in conclusion, the area of the blue right triangle, triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. Okay, so we finished with the second method. In the next step, I will summarize the lecture. We start with the first question, of course. In the first question, we have in the drawing the right triangle, triangle ABC. Side AB equals to 8 units. Angle ABC equals to 90 degrees. We know that BC and AC are integers. And we want to find out the radius of this circle that is described by the right triangle, triangle ABC. So first of all, we define side BC as A and side AC as B, and we implemented the Pythagoras theorem on the right triangle, triangle ABC. According to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. Repeat again, in the right triangle, triangle ABC, AC squared equals to AB squared plus BC squared. AC is B, so AC squared is B squared. AB equals to 8 units, so AB squared is 8 squared, that is 64. BC equals to A according to our definition, so BC squared is A squared. So in conclusion, we found out that according to equation number 1, B squared equals to 64 plus A squared. We subtracted A squared from this equation, and we found that according to equation number 1, B squared minus A squared equals to 64. Then we have the algebraic identity that B squared minus A squared equals to B minus A times B plus A times B minus A. So we substitute B squared by minus A squared by B plus A times B minus A, and according to equation number 1 is equal to 64. We know that AC and BC are integers, but AC equals to A and BC equals to AC equals to B and BC equals to A according to our definition. That is to say, A and B are integers. And because of the fact that A and B are the sides of the right triangle, triangle ABC, of the lengths of the sides of the right triangle ABC, so A and B as lengths, there must be a positive numbers. So from 1 and 2, we get that in conclusion that A and B are positive integers. And because of the fact that A and B are positive integers, B plus A must be greater than B minus A, because when you add two positive integers together, the result must be always greater than the case that you subtract them from each other. So B plus A must be greater than B minus A, and if B is a positive integer and A positive integer, it means that B plus A must be also a positive integer. Here, so we know that B is a positive integer, but here B is the hypotenuse of the right triangle, and the hypotenuse is always greater than the perpendicular, that is to say, B is greater than A. We subtracted A from this inequality and we found out that B minus A is greater than 0. That is to say, B minus A is a positive number. But we know that B is a positive integer and A is a positive integer. So when we subtract one from each other, that is to say, B minus A, if it is not a negative number, then B minus A, if it is a positive, it must be a positive integer. Okay, so in conclusion, we found out that b minus a is also a positive integer. So actually, according to equation number 1, we have here two positive integers that we multiply one by each other, and the result is 64. Then we wrote down all the possibilities that we have for two positive integers that we will multiply one by each other and will give us 64. There are only 7 options here. 1 and 64, 2 and 32, 4 and 16, 8 and 8, 16 and 4, 32 and 2 and 6 and 32 and 2, and finally 64 and 1. Those are all the options that two positive integers, when we multiply them by each other, the result will be 64. But because of the fact that b plus a is greater than b minus a, so b plus a is the first column, while b minus a is the second column. And according to this inequality, b plus a, that is the first column, must be greater than the second column. So, therefore, we will take only the possibilities that the first column is greater than the second column. 1 is not greater than 64, this is not a good option. 2 is not greater than 32, 4 is not greater than 16, 8 is not greater than 8. So all those 4 possibilities will get cancelled. 16 is greater than 4, that is a good possibility. 32 is greater than 2, it is a good possibility, and 64 is greater than 1, it is also a good possibility. In the next step, we will add the two equations, the two expressions together in order to find out the result. Here, actually we added the two numbers together, b plus a plus b minus a. b plus a plus b minus a is b plus b is 2b, and a minus a is 0. So in conclusion, we found out that if we add the two numbers together, we get 2b, that is an even number. Why? Because of the fact that b is a positive integer, it means that 2b must be an even number. That is to say, when we add the two numbers together, the result must be an even number, otherwise it is not a good option. Okay, so we check which couples give us, if we add them together, will give us an even number. Here 16 plus 4 is 20, is an even number, it is a good possibility. 32 plus 2 is 34, that is also an even number, it is a good possibility. But 64 plus 1, it is 65, that is not an even number, therefore it is not a good possibility. So we cancel this possibility, so we left only with two possibilities for b plus a and b minus a. The first possibility is b plus a is 16 and b minus a is 4, and the second possibility is b plus a is 32 and b minus a is 2. So we will focus on the first possibility. Here we will add the two equations together and we get that b plus b is 2b, a minus a is 0, and 16 plus 4 is 20. So in conclusion, we found out that 2b equals to 20. We divided this equation by 2 and found out that b equals to 10 units. Then we have this equation that b plus a equals to 16. We subtracted b from this equation and found out that a equals to 16 minus b. Okay, a equals to 16 minus b, but b equals to 10, so we substitute b by 10 and we get that a equals to 16 minus b, and b is 10, so a equals to 16 minus 10, that is 6. So in conclusion, we found out that a equals to 6 units and b equals to 10 units. Then, according to the second possibility, we have b plus a is 32 and b minus a is 2. We added the two equations together and we found out that b plus b is 2b, and a minus a is 0, and 32 plus 2 is 34. So here we have the equation that 2b equals to 34. We divided this equation by 2 and we found out that b equals to 34 over 2, that is 17. We have the equation that b plus a equals to 32. So we subtracted b from this equation. We found out that a equals to 32 minus b. But b is 17, so we substituted b by 17. We found out that a equals to 32 minus b, and b is 17. So it is 32 minus 17, that is 15. So in conclusion, according to the second possibility, a equals to 15 and b equals to 17. So I drew the two options here. Here, according to the first option, we have this triangle ABC. Side AB equals to 8 units, side BC equals to 6, and therefore AC equals to 10. Okay, inside this right triangle, we have this circle that is inscribed, and we want to find out the radius of this circle. According to the second possibility, AB is 8, BC is 15, and AC is 17. Inside this specific right triangle, we have this circle that is inscribed by the right triangle, and we want to find out the radius of this circle. So in order to find out the radius, the radii of those two circles that are inscribed by those two right triangles, we actually draw the right triangle ABC, that could be any right triangle. Inside this right triangle ABC, we have this circle that is inscribed by the right triangle, and we found out the radius of this circle, and then we use the formula that we found in our specific two right triangles, those two right triangles, and we could use it because of the fact that here triangle ABC could be any right triangle, and especially it could be those two right triangles. So we can use the formula that we will find here for those two, our specific two right triangles. So we found here the formula for the radius of any circle that is inscribed by right triangle ABC. We define AB as A, BC as B, and AC as C. Then we define the point of tendency of tangent AB with this circle as M, the point of tendency of tangent BC with this circle as M, and the point of tendency of tangent AC with this circle as L. Then here we have we define the center of the circle as O. Then we join points O and then together by a straight line. ON is the radius. Then we have rule number 1, that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have the radius ON that is drawn to the point of tendency. Therefore this angle equals to 90 degrees, this angle equals to 90 degrees according to rule number 1. In addition, we have those two, this radius OM that is drawn to the point of tendency. Therefore this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. So in quadrilateral ONBM, we have 1, 2, 3 right angles. The sum of right angles is 270 degrees plus the size of the fourth angle. In total, it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So if we have 3 right angles, then the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in this quadrilateral to 360 degrees. This angle must be equal to 90 degrees. So inside quadrilateral ONBM, we have 4 right angles. Any quadrilateral that those 4 right angles must be at least a rectangle plus a square. So we relate quadrilateral ONBM as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, ON equals to BM. But ON equals to R, therefore BM must be also equal to R. Likewise, according to the rule that the opposite sides of a rectangle are equal to each other, we get that NB equals to OM. But OM equals to R, therefore NB must be also equal to R. So we found out that quadrilateral ONBM is not a rectangle but a square. Then we found out that the length of AN equals to AB minus NB. That is to say, it is equal to A minus R. We found out the length of line segment MC equals to BC minus BM, that is B minus R. Then I presented to you rule number 2, that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. If we focus on the common start point, point A, we have two tangents to this circle, tangent AL and tangent AL. And according to rule number 2, they are equal to each other. That is to say, AN equals to AL. But AN equals to A minus R, therefore AL must be also equal to A minus R. Then we focus on the common standpoint point C. From the common standpoint point C, we have two tangents to this circle, tangent CM and tangent CL. And according to rule number 2, they are equal to each other. That is to say, CL equals to CM. But CL equals to B minus R, therefore CL must be also equal to B minus R. So in conclusion, we found out that CL equals to B minus R and AL equals to A minus R. Then, actually, what is the length of the hypotenuse AC? AC equals to AL plus LC. Here again, AC equals to AL plus LC, but AL equals to A minus R and LC equals to B minus R. So we substituted AL by A minus R and LC by B minus R. And according to our definition, AC equals to C, so we substituted AC by C, and we got that C equals to A minus R plus B minus R. So here C equals to A plus B minus R plus minus R is minus 2R. So in conclusion, C equals to A plus B minus 2R. We added 2R to this equation and found out that 2R plus C equals to A plus B. We subtracted C from this equation and found out that 2R equals to A plus B minus C. We divided this equation by 2 and we got that the radius that we are looking for equals to A plus B minus C over 2. Okay, so now we can implement the new formula. We can use the new formula in order to find out the radii of those two circles that are inscribed by those two right triangles. According to the new formula, R equals to A plus B minus C over 2. A plus B is the sum of the perpendiculars, minus C that is the hypotenuse over 2. So in this right triangle we have R that is equal to A plus B that is 8 plus 6, that is 14, minus C is 10. 8 plus 6 is 14, 14 minus 10 is 4, and 4 over 2 is 2. So the radius equals to 2 units. And in this right triangle, triangle ABC, A plus B is 8 plus 15, minus the hypotenuse is 17. 8 plus 15 is 23, and 23 minus 17 is 6, and 6 over 2 is 3. So in conclusion, we found out that the radius of this circle that is inscribed by the right triangle equals to 4 units, and the radius of this circle that is inscribed by this specific right triangle equals to 2 units. So the answer to the question is that the radius of the circle that is inscribed in the radius of this circle that is inscribed by this specific right triangle, triangle ABC, could be equal either to 2 units or 3 units. We finished with the first question, then I presented to you the second question, and we solved the second question in 2 different methods. Okay. So we have here a quarter circle, and side OB equals to 2 units, AD equals to DO. Inside this quarter circle we have the right rule triangle DBCD, and we want to find out the area of this right rule triangle BCD. Okay. We know that the radius of this quarter circle is 2, so therefore AO also equals to 2, and it is equal to OB. If AO equals to OB equals to the radius that is 2 units, but from the drawing you can see that AO equals to AD plus DO. AO equals to AD plus DO, it is very clear from the drawing. If AD equals to x, then D also equals to x because they are equal to each other. So here we get that x plus x, that is 2x, equals to 2. We divided this equation by 2 and we found out that x equals to 1. So here AD is equal to x equals to 1 and D also equals to 1. Okay, then we completed the quarter circle to a circle, and then We extended side BO by a straight line until it touches the circle at point P. Point O is the center of the circle, point P is the point of the circle itself, that is to say, OP is the radius of this circle that is equal to 2 units. And line segment PB passes through the center of the circle, that is to say, it is passing from point O, therefore it is the diameter of this circle. So PB is the diameter of the circle. Then we extended side CD by a straight line until it touches the circle, and we don't know in which point it will touch the circle, so we will assume that the extended side CD will touch the circle at point X. Okay? So we actually created here peripheral angle BCX. This is a peripheral angle that is equal to 90 degrees, but this peripheral angle that is equal to 90 degrees doesn't rest on the diameter that is PB, and it is a contradiction, because any peripheral angle that is equal to 90 degrees must rest on the diameter. Okay, so in order to solve the contradiction, we must conclude that point X merges with point P. In this case, we have the peripheral angle BCP that is equal to 90 degrees, and peripheral angle BCP that is equal to 90 degrees indeed rests on the diameter that is PB. In this way, we will solve the contradiction. We have here peripheral angle BCP that is equal to 90 degrees, and it rests on the diameter that is PB. Okay? Then we know that PB is the diameter, so it is absolutely a straight line, and we know that the sum of the angles on one side of a straight line equals to 180 degrees. So if we focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees. Which angles we have on the upper side of PB at point O? We have here 90 degrees plus this angle AOP. In total, the sum of the angles must be equal to 180 degrees. So because of the fact that this angle equals to 90 degrees, this angle must be also equal to 90 degrees. In order to complete the sum of the angles here, 180 degrees, this angle must be equal to 90 degrees. So this is the right angle, and the triangle PDO is the right triangle, so implementing the Pythagoras theorem on the right triangle, triangle PDO, PD square equals to DO square plus PO square. In the right triangle, triangle PDO, PD square equals to DO square plus CO square. So PD square equals to DO square. DO is 1, so DO square is 1 square, that is 1. PO is 2, so PO square is 2 square, that is 2. So in conclusion, PD square equals to 1 plus 4, that is 5. We took out all of this equation and found out that PD equals to the square root of 5 units. Then we implemented the Pythagoras theorem on the right triangle, triangle DOB. According to the Pythagoras theorem, DB square equals to DO square plus OB square. In the right triangle DOB, DB square equals to DO square plus OB square. That is to say, DB square equals to DO square. DO is 1, so DO square is 1 square, that is 1, plus OB square. OB is 2, so OB square is 2 square, that is 4. So in conclusion, DB square equals to 1 plus 4, that is 5. So we took out all of this equation and found out that DB, the product DB equals to the square root of 5 units. Then we extended the radius AO by a straight line until it touches the circle at point Z. We implemented rule number 1 in our drawing. In our drawing, we have here rule number 1 states that if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Here we have chord AD that intersects with chord PC at point D, chord AZ intersects with chord CP at point D. Therefore, AD times DZ equals to PD times DC. AD times DZ equals to CD times DP. AD is 1. DZ is 1 plus 2 is 3. CD is the missing line segment. And DP is equal to 5 units. So in conclusion, we found out that 3 equals to CD times square root of 5 units. We divided this equation by square root of 5 units, and we found out that CD equals to 3 over square root of 5 units. Then we implemented the Pythagoras theorem on the right blue triangle, CDB. According to the Pythagoras theorem, dB square equals to DC square plus CB square. dB is square root of 5, so dB square is square root of 5 squared, that is 5, equals to DC square. DC is 3 over square root of 5, so DC square is 9 over 5, plus CB square, that is missing side, so we leave it as it is. We subtracted 9/5 from this equation, and we found out that 5 minus 9/5 equals to CB square. Here we multiplied 5 by 5, and then we divided by 5 in order to have a common factor of this expression. And we found out that 5 times 5 is 25, so we have here 25 minus 9 over 5. 25 minus 9 is 16. So in conclusion, we have 16 over 5, that is equal to CB square. We took out of this equation and found out that CB equals to the square root of 16, that is 4 over square root of 5. Here, CB equals to 4 over square root of 5. Now it is very easy to find out the area of the blue right triangle DCB. It will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. The area of the right blue triangle DCB equals to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. DC is 3 over square root of 5 units, CB is 4 over square root of 5 units, all divided by 2. 3 times 4 is 12. In the numerator we left only with 12, and in the denominator we have square root of 5 times square root of 5 is 5, so we have 5 times 2. 12 over 2 is 6, so in the numerator we have only 6, and the denominator we left only with 5. So in conclusion, the area of the blue right triangle DCB equals to either 6 over 5 square units, so in terms of numbers it is equal to 1.2 square units. Then I presented to you the second method to find out the area of the right blue triangle DCB. Here we already found out in the first method that AD equals to 1 unit, DO equals to 1 unit, this angle equals to 90 degrees, and the radius OB equals to 2 units. The radius is equal to 2 units. The center of the quarter circle is at point O, this point. We completed the quarter circle to a semicircle. So we extended BO by straight line until it touches the circle at point P. Then we extended side CD by straight line until it touches the circle, and according to the first method, the extended CD must touch the circle at point P. We already found out that this angle equals to 90 degrees according to the first method. We define this angle as theta, so this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles. This right angle is 180 degrees, this angle must be equal to 90 degrees minus theta. For the same reason, exactly, in triangle BCB, this angle must be also equal to 90 degrees minus theta. Here, dP equals to square root of 5, and PD also equals to square root of 5. According to the first method, PO is the center of the circle, P is a point of the circle, semicircle itself. This is exactly the definition of radius. So PO is the radius of the semicircle, that is equal to 2 units. Then we proved that the big right triangle PCB is similar to the small right triangle POD. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. Those two angles are both equal to 90 degrees from each other, therefore they are equal to each other. And we have the third angle that is a common angle that belongs to both triangles, so this angle equals to itself. So we prove that all the three angles of triangle PCB can go into all three angles of triangle POD, therefore triangle PCB is similar to triangle POD according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will conclude that PD over PB equals to DC over CB equals to PO over PC. PD is equal to 5, PB is 2 plus 2, that is 4, DO is 1, CB is the missing line segment, PO is 2, and PC is equal to 5 plus DC. Then we derived the first equation from this long equation, that square root of 5 over 4 equals to 1 over CB. Because multiply this equation and found out that square root of 5 times dB times CB equals to 4. We divided this equation by square root of 5 and we found out that CB equals to 4 over square root of 5. CB equals to 4 over square root of 5. Then we implemented the Pythagoras theorem on the right blue triangle DCB according to the Pythagoras theorem. And dB square equals to CB square plus DC square. So dB square equals to CB square. CB is 4 over square root of 5. So CB square will be equal to 16 over 5 plus DC square, that is the missing line segment. So we subtracted 16. dB equals to square root of 5, so dB square is square root of 5 squared, that is 5. So 5 equals to 16 fifths minus DC square. We subtracted 16 fifths from this equation and found out that 5 minus 16 fifths equals to DC square. We multiplied 5 by 5 and then we divided by 5 in order to have a common factor with this expression. So 25, 5 times 5 is 25, and we have 25 minus 16 is 9. So in conclusion, 9 over 5 equals to DC square. We took out of this equation and found out that DC equals to 3 fifths. DC equals to 3 fifths. Now, the area of the blue right triangle will be equal to the base of the triangle that is DC times the height to the base that is CB over 2. The area of the right triangle DCB equals to the base of the triangle that is DC times the height to the base that is CB over 2. DC is 3 over square root of 5 units, CB is 4 over square root of 5 units, all divided by 2. 3 times 4 is 12. So in the numerator we have 12. In the denominator we have square root of 5 times square root of 5 is 5 times 2. 12 over 2 is 6. So in the numerator we left to be only with 6. In the denominator we left only with 5. So in conclusion, the area of the blue right triangle DCB equals to either 6 over 5 units, or in terms of numbers it is equal to 1.2 square units. So in both methods we arrive to the same result. Okay, thank you very much.